Why, hello. You're a bit early. My name's LT, and I'm here to talk to you about derivatives, specifically what they mean for you and me.
I.
What?
The proper way to say it is you and I.
This isn't another cheap English video, Virgil. This is freaking calculus. Screw the English, we need to speak math.
Math sucks. English rules. Well, I'm more partial to Latin myself.
For the last time, you're not a dead Latin poet. You're a fat guy who enjoys pretending to be a dead poet.
You pushed me to my limit.
Ahem, where were we? Oh yes, derivatives. Before we can truly understand them, we must first know what they are. So, what is a derivative, you might ask?
What's a derivative?
It was a rhetorical question, and you already know this. We're in the same class.
I slept a lot.
Wait, then how'd you do on the AP exam?
Well, after they cleaned off the drool, it turns out I got a 5.
I hate you with all my heart and soul. Now get off my set.
Fine.
Okay, a derivative is...
Hey, what are you up to? Fine, I'll leave you alone, you jack.
Okay, let's try this again. A derivative is basically a function that can tell you what the instantaneous rate of change is at any point on the function it is derived from. In simpler terms, at any point you draw a tangent line on the function, the derivative will tell you the slope of that line. The most basic way of finding the derivative of a function, without using shortcuts, is by the limit definition rule.
Wait, where am I?
This is an elaborate dummy that will help us better understand what a derivative is and how we come to obtain them.
No, wait.
Alrighty, let's take a look at his fall. As you can see, we have a position time graph here in essence. He starts out at the top, and as he falls, his position changes according to the time. However, from this graph alone, we cannot tell how fast he is falling at any given time. We therefore have to take into account his velocity, the rate at which he is changing position. If we choose a point close to the original point on the graph, and then average them, we come to an accurate average of what the velocity is, but it does not tell us the instantaneous velocity. The closer the 2 points are, the closer we are to finding the instantaneous velocity. This relationship can be described as f prime is equal to the limit as delta x approaches 0, where f of quantity x plus delta x minus f of x all over delta x is the limit definition rule. F of prime of x is the derivative of f of x, and delta x represents the interval between the 2 points being averaged. As that difference approaches 0, the value of the derivative approaches the instantaneous rate of change for the original point. Solving this algebraically with the original function and applying the limit would result in the derivative function, at which plugging in any x value would result in the instantaneous rate of change at that specific value. Here's an example. Let's assume that, for this case, we have a position function that is simply x squared. When you plug it into the equation, you get f prime of x, which is equal to the limit as delta x approaches 0, quantity x plus delta x squared minus x squared all over delta x, which then breaks into f prime of x is equal to the limit as delta x approaches 0, where x squared plus 2 times delta x times x plus delta x squared minus x squared is all over delta x, and then simplifies to f prime of x equals the limit of delta x as it approaches 0, where it has 2x plus delta x. Then we plug in the limit and we're left with the derivatives of x squared being 2x. Okay, what is it, 6?
Huh? What? Oh, sorry, I fell asleep during your 5-hour-long speech.
It wasn't that long.
Oh, you're right. Sorry, it was about 6 hours. My bad.
Hey, it's not easy writing for a close deadline, okay? Do you know how hard it is to try to make math interesting?
I've derived as much.
That's not even funny, that's just wordplay.
There's a discontinuity with your logic.
I'm not even talking about continuity.
I see you're asserting your power rule.
Okay, that just doesn't even make any sense.
You just got fundamental.
You're done.
Fine, but at least go over shortcuts.
Out. Okay, so we know how to get derivatives the messy way. We plug a function into the limit definition rule and find its derivative with the use of a limit and algebra. But the process is tedious and has foreseeable repercussions of being too inefficient with particularly large polynomials or certain types of functions. Our answer to this? Shortcuts. So, what shortcuts can we rely upon? The first and simplest is the derivative of a constant. A constant does not have a rate of change, therefore when you take the derivative of it, the answer is going to be 0. If you take the derivative of 1, you're going to get 0. The second rule we can rely upon is the power rule. Subtract 1 from the exponent of the variable and multiply the initial value by whatever is multiplying the variable. For example, you have 2x to the third. Apply the power rule and you get 6x squared. 1 is subtracted from the exponent, and the initial value of the exponent, 3, is multiplied by the constant of 2. The third rule is the constant multiple rule, which states that when a differentiable function has its derivative taken, you can take out the constant and multiply it back in after the fact. For example, let's say we have 2x. When we take out the 2 first and then apply the power rule to x, it comes out to 1. We multiply in the 2 again, and we get the derivative of 2x, which is simply 2. The fourth and fifth rules are the sum and difference rules, which state that if two functions within a polynomial are differentiable, then they can be differentiated separately. The sixth and seventh rules, the product and quotient rules, are slightly more tricky. The product rule is applied when two functions are multiplied by one another, such as xy. When this occurs, the product rule states that the derivative of two functions being multiplied by one another is the first function times the derivative of the second plus the second function times the derivative of the first. In the case of xy, the derivative would be x plus y, wherein the derivatives of the individual functions turned out to be 1. The quotient rule operates similarly to the product rule with a few major exceptions. The quotient rule is applied when two differentiable functions are divided by one another, such as x divided by y. In this scenario, the quotient rule states that the derivative of a quotient is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by the square of the denominator. In the case of x divided by y, the derivative would be y minus x all over y squared. And that's pretty much it for derivatives.
What about shortcuts?
Sweet Jesus, where do you keep coming from?
Yeah, actually following you around is just great for my sleep time. I don't know if you know this, but you keep talking into thin air. Puts me right to sleep, it's so boring.
I'm not talking into thin air, I'm making a movie, and I did go over the shortcuts.
No, you went over ways to do deriva whatever stuff quicker. You didn't talk about those trig shortcut stuff.
Spoiler alert, a way to do something quicker is a shortcut. Also, that trig stuff doesn't really count because I'm making a video. I'm not gonna break into song trying to teach whoever watches this video the trig shortcuts. If they don't know the shortcuts by now, they're doomed.
Aw, come on, sing!
I'm not going to sing.
Sing!
No.
You failed my limit test.
Not relevant to my subject at the moment. Alright, let me make this abundantly clear to anyone watching this video. If you show this to the guy who just walked off, I will hunt you down. Do we have an understanding? Good. You want to hear the trig song? Fine. S is for sine that derives to cosine, cosine to negative sine. T is for tan to secant, squared down here in trigonometry. Cosecant is negative cosecant cotan, secant to secant tan. Cotan is negative cosecant squared down here in trigonometry. There, a little song to help you remember. I hope you all get A's, you ingrates.
Ha! I knew you'd sing.
Aw, crap.